aromatic compounds. They are basically the benzene and its compound. So benzene ring is a particularly important functional group found in many organic compounds. Benzene ring, which is denoted by this particular symbol, is found in many compounds that are commercially important, for example, in making of medicine, dyes, plastic, etc. Now, if we talk about aromatic organic compound, the compound of benzene, they are generally known as arenes. They are represented by the formula that's CnH2n-6. So the first basic compound of arene is itself is a simplest benzene. Benzene itself, which is depicted by the molecular formula, that's C6H6. Its molecular formula is 78 and its empirical formula will be CH. This is the structure for a benzene, which actually a chemist known as Kekule, he presented that there are going to be 6 carbon and there's going to be an alternate double bond and single bond between the 6 carbon. So this was a structure which was initially presented by Kekule. And this is another compound, its skeletal structure, which is basically methylbenzene. So these are some of the very commonly known aromatic compounds which have the basic structure of benzene as a functional group, basic structure of benzene present with them. So these are some of the examples of the arenes or the aromatic organic compound. Now let's come back to the structure which was proposed by Kekule, which was basically this is a skeletal structure for C6H6, and he said that there's an alternate double bond between the 2 carbon, and there is a single bond, alternate double and a single bond between the 2 carbon. And this structure was said to be planar and symmetrical, and it was a non-polar molecule. But basically, when they done some analytical research on it, or when they have seen it through X-ray analysis, they have done X-ray diffraction analysis over this benzene structure, which was initially said to be with an alternate double and single bond. They found certain problems related to it. So first problem was related with the shape. Now, as we already know that the carbon single bond, carbon-carbon single bond length and carbon-carbon double bond length is different, and its bond strength, bond length, and they are totally different when there is a single bond or a double bond. So if we talk about the carbon single bond, then the bond length is said to be 1.54 nanometer, and for the double bond it is 0.134 nanometer. But when they have seen this particular benzene structure through an X-ray analysis, they found that all these bonds, whether they are single bond or a double bond, which thought to be the alternate single bond or a double bond, they have the same bond length that was approximately to be 0.139 nanometer. So they all were having a uniform bond length. So this again make them understand that this particular structure which was given by Kekule was actually if you understand that they have an alternate single and double bond, so they actually mean it is supposed to be an irregular structure. But through a X-ray diffraction, they found that this was a regular structure where all the bond length were said to be the same. So this was one problem which they have faced, that they thought that the structure which was proposed by Kekule was incorrect, and there's something else which was basically responsible for the structure. Then the second problem they have come across when they were making the benzene react with certain compounds, very basic compounds. So as they have a double bond, they thought that just like alkene, it'll undergo electrophilic addition reaction. Okay, now electrophilic addition reactions are where if which we have seen in an alkene, that whenever the alkene it undergoes a reaction with hydrogen or bromine or hydrogen bromide, across this double bond the bromine atom get attached and they form the compound something like this. Okay, so but this never happened in the case of benzene, right? So instead of electrophilic addition reaction, the benzene underwent electrophilic substitution reaction. They underwent electrophilic substitution reaction. in which one of the hydrogen was substituted by something which has been added to the benzene ring, or which the new the group which is coming to which was acting as a nucleophile and was attracted towards the carbon double bond carbon structure, or the delocalizing of the benzene. Later researchers has given further explanation to the modification of the calculus structure, as because as I already told you that the calculus structure was a failure because of the previous two reasons. Now they explained that the resonance structure of the benzene, and they said that the double bond of the benzene, it keeps on shifting from between the other two carbon. Now if between these two carbon there's a double bond, so this double bond will shift between these two, and similarly this double bond will shift here, and this double bond will be shifting between the other two. So this structure A has become the structure B, and the structure in A and B, they keep on resonating. These are the resonating structure. They keep on interchanging uh, between A and B, because they keep on flipping and flopping into one form or the other form. So they will be giving us a resonating structure, which can be this particular modified structure. This hybrid resonating structure is our understanding of the current model of the benzene. We see a delocalized ring. This is a delocalized ring of electrons, which is there between the six carbon atoms, the six electrons which are delocalized. The benzene ring with a carbon double bond said to have this with the carbon double bond, which said to have sp2 hybridization, where the unbonded p orbital electrons of each carbon atom involved in a sideways overlapping with the other carbon atom, something like this, right? With the adjacent two carbon in a flip-flop manner. This pi bonding in a benzene ring is very different from the double bond which we see in an alkene. This pi bonding of alkene is only between the two carbon atoms. The double bond between the two carbon atom, it can easily undergo electrophilic addition reactions, where the group or the atoms can easily come join or add on to the two carbon which are bonded with a double bond. But if the same electrophilic addition reaction take place in the benzene with the benzene ring, so that'll basically that'll disrupt the delocalized electrons. These delocalized electrons actually give the extra stability to the structure, because they are flipping and flopping, forming a double bond between the two alternate carbon atom, and that gives the extra stability. But if because of the electrophilic addition reaction, this double bond or the delocalized ring, if when it undergoes electrophilic addition, it disrupts. So disrupted delocalization of an electron will discontinue the spread of the delocalized electrons. This will break down, and that will make this whole benzene ring or benzene less stable. So basically, in order to break this particular delocalized electron, they require at least 150 kilojoules per mole of energy to break this delocalization, which is a large amount of energy. And that is one of the reason again that why the benzene reactions or the aromatic reactions are slow, and they require specified the characteristic conditions, maybe the catalytic conditions or the temperature conditions, high temperature conditions, as compared to the reactions which an alkene undergoes. On the previous slide, we have talked about the hybrid model of resonating structures. This is how the pi bond system it look like. There are six carbons here, one, two, three, four, five, and six carbon. And these six carbon, one electron per carbon, it forms a pi bond. So this is the pi bond between which is formed between the two alternate carbons, right? So there is an electron cloud which is formed above and below the plane of the ring. So this is how it is being formed, right? Now there are three electrons per ring, right? Tend to be present in each cloud area above and below. And because of this overlapping orbital, they are able to move over an entire perimeter of the ring. and this is actually which is known as the delocalization of electron. And the six electron of the p orbital that cover the six carbon, as I showed you here. And this is how the benzene acquire a strong pi bond structure with the delocalized ring, and that gives the benzene an extra stability. Now there is a past paper question which states that it says that describe with the aid of diagram, the bonding and shape, the bonding and shape of benzene. And it's a 5-mark question. Now, in order to answer this 5-mark question, we can state these particular points. We can say that the benzene has an sp2 hybridization. Now, sp2 hybridization means that all the carbon, 6 carbon atoms, they are joined in a ring, right, where one 2p electron remain unhybridized, and which leads to an sideways overlapping, and it forms a ring of a delocalized ring which enrich the electron density above and below the carbon atom. So this is all about the bonding. Then we can further say that each carbon atom forms a 3 bond and 1 pi bond, right? Then further we can say that the bond angle, because they're specifically going to they're asking about the shape and the bonding. So the shape comes because of the bond angle. So there the bond angle between each carbon is 120, and because of that they have a planar structure. And we can also say that they form a trigonal planar planar structure, hexagonal planar structure. And then further, we can say that the 6 electrons are free to move throughout the ring, and thus the pi electrons are forming a delocalized ring between the 6 carbon atoms. So this completely explains the structure and the bonding of benzene. Now, further, we move on to the chemical properties or the physical properties of benzene. Let's have a look at some of the aromatic compounds. Now, this is known as chlorobenzene because chlorine is attached as an atom to the benzene, and its formula will be C6H5Cl because one hydrogen has been substituted by chlorine. This is the skeletal formula for chlorobenzene. So all the skeletal formulas are shown here because majority of the past paper question, they show the skeletal formula only. This is nitrobenzene, where the nitro group is attached to the carbon, where hydrogen was initially attached to it, and now it's been substituted by nitro group. This is known as phenol. So this is your aromatic alcohol, where instead of hydrogen, the OH has substituted it. This is known as benzoic acid. Then the methyl group is attached to the benzene ring, so it is known as methyl benzene. Now here, this particular part is an aliphatic compound. This is chloromethyl. It has been attached to the benzene, so this particular part will show the aliphatic reactions, whereas the benzene ring will undergo the aromatic reaction because of the presence of the benzene ring. So this is chloromethyl benzene. Then this is sometime the benzene compounds are also known as phenyl, and we have an ester group attached to it. So this is known as phenyl because of this benzene ring, and this is known as ethanoate because there are 2 carbon and it's an ester. So that is how it's been named. Now the amine, this is amine group and it is attached to the benzene ring. Again, it has been, instead of naming it like benz or something, it's named as phenylamine. Okay. Then these are some other compounds, like you have when the COH group is attached to it, you call it benzoic acid. But because the two COH they've been attached, and they, when you start numbering, okay, now one more thing, when the group is being attached to whichever carbon it is being attached, you number it as 1. Then you can go it either this way, clockwise, or anti-clockwise. So here I'm going to number this benzoic acid. This carboxylic acid is attached to the first carbon, then 2, 3, and 4. So this is named as 1, 4. dicarboxylic acid. I can also number it from anti-clockwise. If I number it anti-clockwise, then also 1, 2, 3, and 4, still it'll be named as benzene 1, comma 4 dicarboxylic acid. Okay, so this is how we name the aromatic compounds, and these are some very common compounds. Now let's have a look at this particular compound. So this compound is basically methyl benzene, and to this the chlorine is being attached to it. So 1 and 2, so the second carbon the chlorine is attached. So we, like aliphatic compounds, we add them as a prefix, so here as well. So this, the chlorine is attached to the second carbon, so it's named as 2-chloro-methyl benzene. Whereas in this case it is attached to the third carbon, so this is known as 3-chloro-methyl benzene. So these are some of the common ones, and we'll be looking at more of the organic compounds, aromatic compounds in the next classes.